In times of growing energy demand, dwindling natural resources, and the climate change debate, the development of new technologies for sustainable power generation is becoming ever more important. Siemens has been pioneering the generation of wind energy from the beginning. Now, it is time to turn this successful and sustainable concept upside down and take it below the surface of the seas, where the tides provide an infinite supply of clean energy. Just off the Irish coast, the world's first commercial-scale tidal turbine is at work. The power of the ocean and the turbine's advanced technology guarantee a much more predictable energy output than other renewables. Twin 16-meter rotors and horizontal axis to capture kinetic flow. 180-degree pitch control to generate power from flood and ebb tide, providing a predictable runtime up to 20 hours per day. The turbines are permanently connected to the power grid and produce 1.2 megawatts of clean energy that powers 1,500 Irish homes. With no primary cost. Renewable. Reliable. Ocean power is a promising contributor in a clean and efficient energy mix for the future. Turn the tides in power generation with an energy resource that never turns off. Cwieme.
I hope it's given you an impression of the technology we're talking about. Sometimes it's very, at least to me, it's important to visually see some of the things. I've been on the machine for a number of times already, and it's a different experience each and every time, of course, depending on the weather. If you have really some gale force winds there, it's really challenging climbing up the machine and back down inside. That's a very, very rough environment. And to share with you some of I'm going to take you through some of the technical specifications. I'm going to try and leave some time at the end for questions. But just to give you an outset of what our challenges are, what we're looking at the moment, what we're confronted with, where are we going, and what have we done. Just a very brief background, because I can take you through half an hour's worth of Siemens, what we're doing within Siemens, etc., and where we organized. I've decided not to do that. I expect that there's a lot of people interested in copper winding, coils, generators, these type of things. So taking you back 100 years, I come from an organization that's called Hydro and Ocean Power. It just happens to be organized together for very good reasons. And we have a business that has more than 100 years history. In fact, the pictures that you see there is still a working a power plant. Some of them are actually as old as 100 years. Of course, in today's terms, they have nowhere near the efficiency that we're looking for today, but those are really, really reliable, long-term working power plants, renewable power plants. Siemens' exposure in hydro is basically three activities. You may be aware, starting from the bottom, that we have a joint venture with Voith called Voith Hydro. I think the Americans call it Voith Hydro. The Germans would call it Voith Hydro. We have 35% shareholding. They run the business. They do large and small hydropower plants the world over. I think they've done something like 300,000 megawatts worth of installed plants. And it's approximately $1 billion business or €1 billion business annually. Then we have on the top the small hydropower plant business that we take care of, based out of our competence center in Austria, in approximately a dozen countries, and ever growing, where we look at small hydropower plants of turbine sizes up to 30 megawatts. That's the picture that you saw, is a small hydropower plant. And what we're going to talk about this afternoon is marine current turbines, a business of which we are the owner. We bought up 100% of the shareholding early last year. We've been involved with a minority stakeholding since 2010. So for the last 3 years we've accompanied the development. and late in 2009, early 2011, 2012, we decided that the challenges were so great and the requirements were so important that we would probably be best off taking charge of those as Siemens 100% ourselves and buying out the other minority shareholders, just simply because the amount of financial requirements in terms of research and development were exceeding their interest to participate, if you like. The specific project, Strangford Loch, and you saw some good live films, videos, is based in Strangford Loch. For those of you not too familiar with that, the northern part of Ireland, Northern Ireland in fact, just southeast of Belfast, somewhere between Great Britain, if you like, and Ireland. There's a loch, a bay, with an opening channel. This is the opening channel here, through which all of the water flows in and out every time the ebb tide and the flood tide change. That happens twice a day, so you have water moving backwards and forwards here in this channel twice a day. You saw some of the forces and the movement speed of the water in the film at the bottom of the machine, and this water moving in and out twice a day is what we use to generate electricity. And you saw the blades turn to pitch so that we can use the same machine without turning all the drivetrains to produce energy as the water flows out of the loch and back into the loch. At this particular site, which is a very, very good site for energy generation, we produce up to 20 hours of predictable energy. Effectively, you could say it each and every day from when to when you will be producing energy, because you know that the water will be flowing in and out. It's very dependent on the moon cycle. For those of you, when you go to the beaches and you pay attention, sometimes they have these blackboards that can tell you today the high tide will be at 6:42 and low tide will be at 12:32. Well, it's exactly with that precision that you could say from 11:28 this morning until whatever 13:25 you can produce so much energy. Then the water turns, there's no energy there while the water turns around. As it moves back, you can then again produce from 14:23 until 4:30. Then the water turns again, you have a slack period. So you have very predictable energy generation. And as I said, 20 hours per day worth of energy generation. Some of the data, I'm not going to take you through of it, but it's a bay, an inland bay where a lot of water flows in and out. That makes this such an attractive site. What made this site specifically challenging for us, and this is one of the learnings, it's evident if you're in a pioneering environment, is we were confronted with all the environmental requirements. This is a European National Habitat Zone. There's quite a couple of seals, special seals and porpoises, and we had quite extensive environmental testing and monitoring to go through. This machine, as it says here, has been running. It's been running for 5 years. It still runs today. Every second Monday morning, I'll get a report saying how much energy we've produced in comparison to what we were expecting to produce. And then there's sometimes reasons for why grid's been down or whatever, why it hasn't produced. But on average, we can produce somewhere around 200 kilowatt hours in a 2-week cycle. Unless, of course, we have planned maintenance and scheduling, etc. We take the machine up. Some of the pictures that you saw, the machine, the cross beam was raised above water for servicing purposes. Here's some of the technical details, and in the pictures you can see that this is the crossbar raised above the water so that we can do service work, inspection to see how the machine's performing, whether any bolts are loose, whether anything's happened, contacts are loose, cables, etc., etc. So we have two axial flow rotors, the diameter of each 16 meters, capacity of 600 kilowatts per drivetrain, so 1.2 megawatt machine. That's what it produces nominally. The moment we hit 2.4 meters per second, and you remember I said a few minutes ago that we can predict when the water will exceed that speed. It is known, the cycles are continuous, depending of course on the lunar cycle. But we can say for how much time a day the water will be above the speed. We can predict for the next year how many hours the water will be above this nominal speed, hence what is the potential of generating at nominal capacity in next year. So we can feed up to annually at this particular site, because we have got the lengthy measurements now. We have a reasonably reliable prediction database to say how many hours we will produce energy. We can produce up to 6,600 megawatt hours of electricity into the grid. It covers about 1,500 homes. That's quite convenient because there's two villages on either side of this loch, and they can both be served with electricity. It's capable of delivering 10 megawatt hours per tide. It's actually per tidal cycle, so it's an ebb-flood cycle, and effectively you have 2 of those per day, so we produce 20 megawatt hours per day. Oh, I could do that here. I was expecting a very technically oriented audience, so I hope I'm not going to bore you with too much technical details, but I know that engineers sometimes like to have some facts and figures, so there's some more facts and figures for you. The tip speed is relevant, of course, for the questions. Do we chop suey fish that come through? No, the rotors turn reasonably slow. They turn around 14 to 15 times per minute, so you can actually see the rotor turning, the blades turning. No fish or anything has been damaged yet. They know how to get away or avoid the machine. The blade pitches through 270 degrees. If you saw in the animation earlier on, as the tide changes from ebb to flood tide, the blades pitch in a different direction so that the machine stays in the very same position and produces energy in both moving directions. So all we do is at the root here of the blade, we pitch it and it turns to produce energy out of both directions. 30 meters across, that's the crossbar here. I think if I remember correctly, just under 200 tons that we lift out of the water with the rotors intact. And we have a hydraulic lifting system that jacks up during a slack tide which is normally around an hour or so. We can pump it out of the water to do service. We then obviously, while we're doing the work for let's say an hour, 2 hours, we inspect, check some of the things. We lose half a tidal cycle, and then we can drop it back down and carry on producing in the afternoon. We've done some film footage as well for German television. For those of you that are interested, I think Bayern BR3 and Vox have done, if you want to Google, Vox have done some film editing on the machine, in fact for some service work that we've done. Here are some of the challenges, some of which I may have referred to, and I'm definitely not going to mention all of them, but you can imagine I mentioned that we need increased investments. What we've discovered in the ocean industry, it's good, and I was asked again this morning, it's good doing simulations, and you do engineering simulations beforehand, but you need to actually spend the money, go out, put the machine into the water to actually learn what actually happens. Because as with many things, reality is somewhat different to what your simulation environment looks like, just simply because we have very harsh conditions. We've had some discussions with experienced guys from floating platforms, offshore oil and gas platforms, and they cite a very respectable statistic that says if you take an onshore wind farm or an installation cost and you try and take it offshore, you must calculate approximately factor 10 of complexity and costs of actually installing it. If you want to then go and do it subsea and go and install a machine subsea, you can expect for it to be at least 10 times riskier still. So the installation per se is very, very challenging, because remember, as it is predictable, this water is moving twice a day, so you don't have much time to do it, so you're actually working in a dynamic environment. I can tell you, offshore wind farms, the guys don't put up these wind farms at the strongest wind conditions. It's just too dangerous. We don't have a choice here. Of course, we'll try and use those weather periods where there's not too many waves around, because that again is a complexity and challenge in health and safety. So we try and use the summer window, which the wind offshore guys do as well, where the wave conditions are better. But we have the steady flowing water, which is good, it's predictable, but we also have it for installation, which makes installation challenging. We cannot find a window when the water does not move, because then we're in the wrong place in terms of production in the first place. Our challenge today is this particular device has been in the water 2008. I said it's cost tens of millions. We're in the process of developing the next generation, because obviously this particular device is not cost competitive today. It's the first device, it's a prototype, it costs a fortune to put in. We're learning. The next device will become more cost competitive, and so this industry will have to prove that ultimately it can live without subsidies. Because if I follow political discussion, none of us want to pay subsidies forever. So effectively, even the renewable energy at some point in time has to be cost competitive with other substitute energies. That's really the target. Now, at the moment, that is extremely ambitious for us in the ocean power industry. Our midterm target for the next decade is to meet the offshore wind technology price level, and then to get down on the cost curve and to make this a competitive, reliable renewable energy. We're looking at some new designs. I'll show you a picture of what our next generation will look like. We have to work very hard with politics, stakeholders and customers. Stakeholders, of course, the fisheries, the environmentals, the local population, all people that may have or may not have concerns, the guys with the grid to export the energy into for distribution purposes. We need the political support. Obviously, we need subsidies. We need an environmental tariffs to make this industry happen, and we're working in some of the designated regions where that is a possibility. The UK is very advanced, in particular Scotland, but also the rest of the UK doing very well. France, Canada are being very aggressive, and the Japanese are also discovering that post-Fukushima they have quite a bit of tidal potential, but in the past they've had at least not too much ambition to exploit this, but they're also awakening to this because they have a potential of 40 or 42 gigawatts around the Japanese ocean or ocean side that they can actually tap into for their use. It doesn't cover all of the Japanese energy requirement, but probably can generate as much as half of their specific potential requirements. Sorry. What have we achieved so far? We've produced more than 7 gigawatt hours of energy that's actually been fed into the grid. We're approaching 8 gigawatt hours. I'm not quite sure. It'll probably happen somewhere this week. I didn't work it out exactly because these statistics become less important when the first gigawatt hour was important, then 3 was, and then 5, and then we stopped communicating each and every time. As I said, it's been up and running for 5 years. We're looking at an extension to have it running for another 5 years, because it's the first and the only real reference plant in the ocean power industry. It's very attractive for the public and the industry and even competitors, but customers as well, to come and visit and actually get a feeling of what this is all about. It's been proven. I've gone through all of that. We've gone through the full environmental monitoring cycle. A complete report was issued in January of last year by Queen's University Belfast and other entities that did the monitoring. It was an expensive exercise for us, but it was necessary, and it helps us now to claim that there is no or negligible environmental impact. Effectively, the seals of the region have increased in population. Why? There's a heat exchanger in here. At the bottom there's some mollusks, some shells, etc. that are settling down. They found extra space just other than the seabed. That's good. So there's shellfish there, there's lots of small fish. With the small fish come the seals come, because they think each time when the water stops moving, that's good feeding ground for these guys. So they're quite lazy. They just sit there on the side. There's a little rock in the river. They just lay there and wait for the tides to stop turning, and then they know they can just go and feed there, and then they go and lie down again and bathe in the sunshine. So it's effectively had a positive impact on the seal population. I don't want to say that too loud, because the fishermen are not too happy about that. They prefer to have less seals there because they eat their fish. But from the environmental monitoring point of view, it's been negligible. Something's happened here with the animated pictures here, so excuse that. There's supposed to be an error here. We're not trying to black out something here. It just looks a little bit different on this computer screen. This is what we're doing. This is the next generation. It looks a little bit similar. For the detailed analysis, effectively we're now working with 3 blades. Why? This machine is designed for a 20-year lifetime. The prototype was not. So with a 20-year lifetime, we have analyzed, and we know from experience that the loads on the structure, the turbine and the bearings in here will be smoother from a 3-bladed machine. It's a little bit more expensive. There's a minor gain in efficiency. The bottom line is there's no real economic reason to do it other than the longevity of the bearings and the machine. So for a 20-year lifetime, 3 blades is better. We've also changed slightly the base foundation. We have a tripod. The other machine that's in reality being built is a quadrupod, which means it's got 4 pin piles. This one will only have 3 pin piles. We're working towards a 2 megawatt. In fact, the drivetrains are being built. They're going to be going into accelerated lifetime testing. We're going to comprehensively test this machine before it goes into the water in 2014. It's going to go through an extensive set of tests before we then build them for the next project, which is going to be probably 5 2 megawatt machines in Wales. We have all the consents and grants are there. We've won a MEAD fund. For those that are not out of the industry, it's a UK fund. It's called Marine Energy Accelerator Deployment. I hope I got the abbreviation right. A fund which is a £10 million grant awarded to support the first project, to help the project be financially viable and get going. I've spoken about this. Increase the project economics. I've explained the pitch system effectively, which not only adjusts to the flow of the direction, but it also helps to manage the loads. So when the 2.4 meters per second water speed is reached and we produce at nominal capacity, this machine will be the same. We then produce 2 megawatts, one on each powertrain, 1 megawatt, 1 megawatt. Then the pitch starts turning in slightly, as within wind power turbines, so that we only produce 1 megawatt. We don't want to produce 1.5 megawatt, when theoretically we could, but the machine is laid out for 1 megawatt. It means it takes the loads of 1 megawatt's energy generation, and we regulate the amount of energy it absorbs out of the potential energy in the water. That helps keep design specifications under check. Otherwise, you'd have to design for a potential 2 to 3 megawatt when you're rarely going to be producing 2 or 3 megawatts at any particular site. So that's the pitch system, which works very well on this machine, very similar as in wind turbines. One of the design specifications, it has to be cost effectively maintainable. We need to be able to change any component on this machine within 48 hours. Now imagine these machines are about 2 to 3 kilometers offshore. We've got to bring it up. We've got to be able to take off. In the worst case, we'll take off the complete drivetrain, take it off the machine, take it to shore and put a new one on in a matter of 2 days. Why? Because once you've paid the money you want this machine producing, you want it to produce. You don't want it to be sitting ashore for repairs, you want it to be producing. So that's design specification. And the cost of the operation of getting a ship out there and doing the work needs to be below £10,000. Some of the technologies that have been developed, they just dump it on the bottom of the sea, and they have to take an extremely expensive ship to recover the machine, and the ship costs you something like £100,000 per day. And if you have to go and pick up the machine, take it to shore, that's a minimum a day. When you fix it and you've got to put it back out, that's another day. So you're looking at $250,000 up to $500,000, and some have even paid $1 million to have their machine brought back to shore and repaired and put back out. So that was important for us, the serviceability of the machine, so that we can actually operate it.